Let's try it again here. We're talking chapter 16, and obviously, as we just mentioned, pH scale 0, 7, 14. Again, less than 7 acidic, above 7 basic, and at 7 they're neutral. We talked about a couple of ways to kind of get all these sort of calculations. We have our Kw, which is really like a constant, concentration of H plus times concentration of OH minus, and that equals 1 times 10 to the minus 14. We could use that if we have either the H plus or the OH minus concentration. Or again, remember H plus, H3O plus, same thing. You could use that to compare the concentrations, and if the H plus concentration is larger than the OH minus, then it's acidic. If the OH minus is larger than the H plus, then it's basic. And obviously, if they are neutral, they will equal each other, which will equal 1 times 10 to the minus 7. That would give us a pH of 7. To calculate the pH, that is minus the log of the H plus concentration. A similar sort of scale is the pOH scale. And again, here we use OH minus there on that scale, as we talked about. And the nice relationship between these two is if you take the pH plus the pOH, that will equal 14, which does give you a little bit of variety, thank you, in terms of maybe how you could calculate things. We also saw that if you do have the pH given to you, you can directly calculate from that the H plus concentration, and that is the inverse log of the negative pH. And again, as we talked about last time, on most people's calculators, when you hit the inverse log, which is usually the second button or shift button top left corner and the log button, it'll put a 10 and a caret up on your calculator. And again, you want to make sure you use the negative, not the subtract button in all of these, to turn it negative as well. You also could get from the pOH, you could get directly from that the OH minus concentration. It is really the same calculation, inverse log of the minus pOH. And again, that should give you a 10 and a caret pOH. A reminder again that if you're asked, is it acidic, basic, or neutral, it is just one of those answers. And I would highly recommend probably always looking at the pH value if you have it. And that's because this is the scale most people have in their head. Again, as I mentioned, a very common mistake people make is they calculate the pH, then they calculate the pOH, and they go, cool, one's above 7, so it's basic, and one's below 7, so it's acidic for the same solution. So it can only be one of those answers. Always look at the pH, and that's usually the good move. Any questions on that there? All right, so I think we did an example. Do a couple more examples here. What is the pH? The pH is 3.14. What is the H plus? Let's just do it all to make sure our calculators work. What is also the OH minus concentration? What is the pOH? And is it acidic, basic, or neutral there? Okay, so let's take a look and see. So in this case, you do have a couple of options since we're going to be looking for everything. You obviously can answer the original question, which is what is the H plus concentration? And you could get that directly from the pH because you have that, which is 3.14. You could also get the pOH since we're looking for that as well by just subtracting 14. So we'll start with the H plus. And again, the H plus is the inverse log here of the negative 3.14. Again, on your calculator, probably looks something maybe like this if you punch it in. And if you do that, remember we also talked about depending on the type of calculator you have as to how you need to punch it in. If you have a display calculator, shift log negative 3.14. If you have a non-display calculator, 3.14 negative button, and then second and log will get you there. This should get us a, we'll call it 7.2 times 10 to the 1, 2, 3, 4, minus 4. Does need units as it is a concentration. 2 decimal places, 2 significant figures going backwards in terms of that. We also could get the pOH, which will basically equal 14 minus the pH. So that's going to be 14 minus our 3.14. That's a 1086 on our pH here. We can also get the OH minus at this point two ways. You could do the inverse log of the POH. You could also go back to KW if you liked as well. You can do just a regular KW sort of deal to get that. And that would be, we have 7.2 times 10 to the minus 4. And I'll get you something like 1.4 times 10 to the minus 11 molar. Again, you could also have done the inverse log of negative 10.86. Or write it correctly there, 86 there. And that should also get you there as well. So there's a few different ways you do it. In this case, we're looking as to whether this is acidic, basic, or neutral. This should be acidic based off of the pH here, yeah. Any questions on any of those calculations? All right. All right, so do this one here. We'll just do what it says. What is the OH minus from the POH of 5.67? Okay, so obviously here we have the POH, and again, from that, it tells us we can get the OH minus directly, and that is going to be, again, our inverse log there to get the concentration, negative pH, 5.67. So again, probably like something like that on your calculator display. And that's a lot of zeros. Oh, I'll do that. All right, so I'll go 2.1 times 10 to the minus 6 molar. Again, two decimal places, two significant figures as we go in that direction there. Any questions on that one there? So let's talk a little bit about what happens if we want the pH of a strong acid. And if we want the pH of a strong acid, because it's a strong acid, it will 100% break apart into ions. And remember that there's sort of a list of kind of 6 strong acids that's really good to know. And again, hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydriodic acid. So when we have something like HCl, it will, as we've been talking about, completely break apart into solution as H plus and Cl minus. And if we were interested in the pH of this solution, it is the H plus that's of interest here. And if we had, for example, this, which is this concentration is 0.1 molar, as we talked about in the solutions chapter, we could kind of do a little stoichiometry. It's a 1-to-1 relationship between those two. And that means that the concentration actually of the H plus in that solution would be 0.1. And that's really all we would need at that point to calculate the pH. The pH there is negative log of 0.1. And that's going to get us a pH of 1 here, I believe, which is acidic. So the good news about most strong acids are they are monoprotic, which means if you know the concentration of the acid itself, that essentially is the H plus concentration. So you could go right into the pH and not have to worry about it. By the way, this works very much similar with bases. So if you had strong bases, remember that our strong bases, a lot of them are from group 1 and 2 on the periodic table. So again, like our lithium, sodium, potassium, hanging right there, calcium, strontium, barium, as we go through there. These guys with OH in it is typically our strong bases. So if you had something like sodium hydroxide, which is a strong base, and it broke apart into sodium ion and hydroxide ion, and let's just say that this guy was also zero point 0.1 molar. In this case, we don't have H plus because it's a base, but we do have hydroxide, which is obviously part of ways we could get to pH. So we could do that. A 1-to-1 relationship here means that the hydroxide concentration in this case is 0.1. That would allow us to get not the pH, but again the pOH here, minus the log of 0.1, going to give us a pOH of 1, which definitely is not basic, but if you thought that was a pH. But the pH here, 14 minus 1, would give us a pH of 13, which is obviously definitely basic here. In this particular case, they're both really basic, but again, if you thought the pOH was the pH, obviously that wouldn't be basic. So we could also do this type of thing as well. So if you're looking for the pH of either a strong acid or a strong base, for the strong acids, you basically just need to get the proper H plus concentration, and you could go in there. And if it's a strong base, you need the hydroxide concentration, which will get you, again, not the pH directly, but you can get the pOH and very easily get to the pH. Now, if it's a weak acid or weak base, well, you just wait until you take 1B, and then you'll learn how to do the pH with those guys at that point. So you can probably safely assume if you see something in this class, it's most likely a strong acid or strong base if you're asked to calculate the pH in this case. So this would be a case, again, if you're given a formula, instead of just a generic H plus or OH minus concentration, probably in this class you safely assume it's probably strong, and that's the way that you would get the pH. Any questions on that? Yeah.
Their ion, chlorine would be diatomic, it would just be chloride by itself.
Yeah, so if you're asking, is the Cl on the right-hand side Cl minus? It is, because it's in a solution. And that's basically what makes it pretty much an acid or a base. It has to be in a solution. And in a solution, chlorine is basically the chloride ion floating around. And chlorine by itself is actually a gas, and it wouldn't be in the solution at that point. Yeah, as that form. Yeah. Any questions on that? All right, so why don't you try these two? What's the pH of each of these solutions? See what you come up with. Okay, so let's take a look. So first one, again, is perchloric acid. And that is on our list of 6 sort of strong acids. So we know when we do have perchloric acid in solution, it's not going to stay together. It's going to completely dissociate or break apart into H plus and perchlorate here. Once again, as we talked about a second ago, really the important thing here for pH is the H plus concentration. And in this case, as most strong acids are, it is really a 1-to-1 relationship between these two. So again, the concentration of H plus is 0.025. And at that point, that again is really all we need to go into our pH. So our pH here is going to be minus the log of 0.025, obviously from there. And that's going to get us a number here with a few digits. 1.60. That is definitely acidic, which makes sense since that is an acid, right? So that's all good. Again, if you got a basic pH at this point, you probably did something wrong, I'm assuming here, since this is a strong acid. Any questions on that one there? On the bottom here, we definitely don't have an acid, right? Because it has hydroxide, so that should make you think base, right? At this point. And really, calcium there is one of those group 2 guys that, as I just mentioned a second ago, kind of your lithium, sodium, potassium hanging right there at calcium, strontium, barium. So that's going to be a strong base is basically what we got going on here. So we got really a strong base. So just like the acid, as I mentioned, it will break apart, and we would have calcium hydroxide here, and it's going to break apart into a calcium, and it's actually going to break apart into a couple of hydroxides, right? Because it's got a 2 there. And that's kind of important here because we are interested in this case, the hydroxide concentration. Again, that's not going to give us the pH directly, but it will allow us to get to the pOH. So in this case, though, this is 0.0255, if I write the 5 molar. That's a very bad 5, I'll put it underneath. And it is, though, a 1-to-2 relationship here. So as we talked about with ions and sort of molarity, we basically actually need to multiply that concentration by 2 to get the proper hydroxide concentration here. So that would be 2 times 0.025 molar, going to give us a 0.05 molar. And that would actually be the correct concentration here of hydroxide, as we talked about when we were talking about ions and concentration. Basically, when this would go for a swim, you're going to get a calcium ion and a couple of these ions. So it's twice as concentrated in terms of hydroxide as it is calcium. And again, that is how the molarity changes. Remember that if it breaks apart into like a 1-to-3 relationship, you would multiply by 3 and so forth. So you can kind of multiply by the coefficient. That's why up here we really didn't multiply by anything, because it's basically multiplying by 1, because it's a 1-to-1 relationship. So here, that's going to give us, once again, though, not the pH, but the pOH, and that's going to get us 0.05, and that will get us 1.30. We now then can get the pH by simply taking 14 minus that. Well, 1270, we'll call it. And 1270 definitely is basic, right? So again, we get to a good one. I would say out of the two, probably the basis is the one sometimes you have to do that for and adjust, again, because most of your strong acids are monoprotic, so it'll just produce basically 1H plus in most cases. So usually the base is kind of the only one. In this situation, you would have to maybe worry about it. And not in all cases, obviously, like the one we did previously with sodium hydroxide, it was a 1-to-1, so you didn't have to adjust it or anything like that. Any questions on pHs of strong acids or strong bases? All right, then that leaves something, maybe buffers. So let's talk about buffers. Good talk. Let's talk a little longer, maybe. A buffer solution is one that can actually resist changes in pH when you add acid or base to it. So sometimes people have a misunderstanding about what a buffer is, and sometimes people think a buffer solution is a neutral solution. And a buffer solution can definitely be a neutral solution. It could also be an acidic solution. It could also be a basic solution. You can make a buffer at any pH you like along the pH scale. You could actually make it at any pH you want. What a buffer actually is a solution, for example, that let's just say you made a buffer at a pH of 5. And that means that if you took that solution that you made at a pH of 5, that's a buffer, and you added additional acid to it, it basically would hang out around 5. It wouldn't have a very big jump in pH. Maybe it goes down a little bit, maybe it goes to like 4.9 or something like that, but it will not go from like a pH of 5 if you add acid all the way down to like a pH of 1. So you won't get this really big jump in pH when you add acid. Same thing if you had that same buffer to start with and it was a pH of 5 and you added some base to it. Maybe it goes up a little bit, maybe it's like 5.2 or something like that, but it will not go from like a pH of 5 to like a pH of 12 if you made the buffer correctly and what you added was okay. So what a buffer is a solution that has the ability to resist really big jumps in pH when you add additional acid or base to it. It basically is able to stay sort of around the pH it started at. The reason it's able to do that, as we'll talk about, is really what a buffer is made out of. And a buffer is made out of really one of two combinations. One combination is up there. You could either have it made out of a weak acid, and it's sometimes referred to as the salt of its conjugate base. That just means it's got like a sodium or something hanging out doing nothing. It's an ionic compound, basically. Or you could actually make a buffer out of a weak base and its salt of its conjugate acid. So they both need to be in the solution together, and that is how a buffer is able to actually function. You cannot have a buffer that's made of a strong acid or a strong base. So if you have a strong acid or you have a strong base, there is no way for that to really be a buffer at all. So it cannot be a buffer if you have those things. Not really important for our class, but you can actually make a buffer as a result of a reaction, but of a strong acid or a strong base, but they are gone at that point. The buffer itself always has to be weak. So why does a buffer have to be weak acid or a weak base and not a strong acid or a strong base? It's because the functioning part of a buffer, for example, if we call this an HA an acid, and A minus the base, what it needs to do is have both of those things in the solution at the same time. So when you make an actual buffer, in order for it to work correctly, you need to have basically an acid part to your buffer, and you need to have a base part to your buffer. And they need to be in that solution floating around together, and that works really well for it to be a buffer. So for example, if you took the classic example everybody uses, which is acetic acid and sodium acetate. This is a weak acid, and this is basically conjugate base or salt of its conjugate base. What makes it a salt? It has the sodium. The sodium really is not doing anything here. The actual buffer components is the acetic acid, and it's actually the acetate part here. It is not the sodium part. That's the conjugate base. What is that relationship? That is the same acid conjugate base relationship we talked about with Bronsted-Lowry. The only difference is 1H plus. Yeah. So that is the only difference between acetate and acetic acid is 1H plus. And acetate or acetic acid is a weak acid. Why is that important? It's important because when you put acetic acid into that solution, it is a weak acid, which means it's a weak electrolyte, which means it will actually set up in that solution an equilibrium. And it basically will be in there, arrows and all, not really, but we'll put the arrows in the beaker as well. And it will basically will set up this equilibrium because it's a weak electrolyte. Remember those kind of arrows heading in both directions. And what that's able to do, because it can set this equilibrium up, is it keeps the two things that you need for this to be a buffer in the solution. You have acetic acid and you have acetate, which is really your buffer part here. And again, that is the acid part, and that is your base part of your buffer. Now, how do we get those? Well, you throw some acetic acid in like you did in that experiment, right? And you throw some sodium acetate in there, which is basically your source of acetate. And that's how you made that buffer that resisted change, right? After you added 4 million drops of whatever you were adding to it, right? And that's what makes this buffer fully functioning, is having both of those things in the solution at the same time at pretty good concentrations. And that's why you add sodium acetate in there and not just acetic acid. Acetic acid will produce some acetate when you just by itself, but it won't produce enough to be an effective buffer. So that's why you add a little bit more sodium acetate in there to kind of beef up the acetate part of the buffer. So now you got both parts in there at pretty good concentrations, and it'll be able to really function as a buffer and resist really big changes. Why can you not make a buffer out of something that's a strong acid or a strong base? Let's just take hydrochloric acid as an example of that. Hydrochloric acid, as we've been talking about, would break apart into H plus and Cl minus. This is our acid, right? And really, this is our conjugate base, right? Which, as we just talked about, you need both of those things to be in the solution for it to act as a buffer. The problem, though, is when you dump HCl in, it's going to completely break apart right into these ions. And that means that the only thing you'll have in your solution is H plus and Cl minus. You'll have the base part, but you'll be missing the acid part, right? And that is why a buffer cannot be made up of something that is strong, because you can only get one part of the buffer in there and keep it in there. You won't be able to ever get both parts of the buffer in there that you would need, and that's why they cannot really make a buffer out of something that's strong. Same thing would happen with a base. If you did sodium hydroxide, I don't know, you could get some of it in there, but you will not be able to get the other part that you need. So a strong acid, strong base can never be a buffer. Weak acid, weak base, and its conjugate partner can be. So when you're trying to determine if this thing can be a buffer, for example, if you can make a buffer out of something, the two things that you really want to look at, I would say at this stage for you, is are the two things related to each other based on Bronsted-Lowry? Are the only difference really an H plus? Now, keep in mind that with a buffer, you'll have salts, which means you'll have an extra sodium, an extra potassium, lithium, something like that. And that's not really the important thing. So here, when we look at sodium acetate, this guy is the important part. The kind of spectator ion is not really important. And this guy is the important part. And those two things, again, are related to each other. The next thing that you would want to look at is the acid or the base that you're trying to make your buffer out of. Is it a strong acid? And that's what I would look at first, because there's only 6 strong acids, which means it's very easy to know is it a strong acid or not. And pretty much if it's a strong base, it'll have hydroxide in it. So these are ways you can quickly go, okay, that can't be a buffer because it's strong. You can't eliminate it. And if it's not, then you can put it in. So for example, if I want to make a buffer out of HF and potassium fluoride, could I make a buffer out of this? HF is what type of acid? It is a weak acid, so that's good, right? Are these two things related to each other by 1H plus? The answer is yes, they are, because KF is a salt, which is K plus and F minus. So this is a spectator ion, kind of like our sodium, that's not important. Now is HF and F minus related to each other? Yeah, that's your buffer right there, yeah. So sometimes people think it's not because the kind of conjugate guy has some type of like spectator ion in there. And very commonly it's a sodium, a potassium, something like that, maybe a lithium sometimes. And if you get rid of that, what you want to look at is the other part of it, and that is really buffer. So this actually would be a buffer system that you could do. Same thing, you know, if you had something like this, right? This is bicarbonate and carbonate, which is a buffer. They're related to each other by 1H plus. But sometimes this would be written NaHCO3 and maybe Na2CO3. This again is the exact same thing, except the sodium is just not doing much. Yeah. So sometimes people kind of miss that it can be a buffer because it has those extra kind of sodiums or potassiums in there. So ultimately, we want to think about kind of what is the sort of functioning part of the buffer. So because it has to be like an acid-base combination, you need something that has one more H plus than something else, right? And that are related to each other. So when we look at this and this, it's got one more H plus than the other guy. This guy here and this guy has one more H plus, and obviously our acetic acid and sodium acetate have one more H plus, and they are related to each other. So you want to always kind of pick out the buffer part of it to make sure it is. I would say probably safely you can eliminate anything from group 1 that's in the NA formula and just kind of look at what else is there besides the group 1 guy. And then you probably be able to see if they are related to each other or not. Any questions on that? Yeah.
Just to clarify, base and weak acid.
No, so you have to have a combination of one of two combinations. One combination is either you have a weak acid and its conjugate base, or you could actually have a weak base and its conjugate acid. So, but you have to have either a weak acid and its partner or a weak base and its partner. You don't have both weak. So yes, that makes sense. So for example, an example of a something like this, NH3, NH4Cl. This is a buffer or not a buffer? It is, probably because I said let's take a look at one, but it's that is NH3, which is a weak base. This is a salt, right? And this salt's going to break apart into NH4 plus and Cl minus. In this case, the Cl minus is not important because this guy and this guy are related to each other, and that's going to be your buffer there. The difference between those two is only a H plus in this case, yeah. That's ammonium. This is ammonium, a polyatomic ion. This is ammonia, which is actually a weak base. And it's a weak base because, as we talked about, most strong bases will have hydroxide like on them, like sodium hydroxide, potassium hydroxide. They'll actually have hydroxide in the formula. And that's usually what makes something like kind of like a strong base because it's essentially carrying the hydroxide with it. So all it has to do is go for a swim and it will release the hydroxide. Something like ammonia actually has to go find water and do like a little reaction to produce the hydroxide. And that's what makes it a weak base, yeah. So this would also be a perfectly fine functioning buffer in this case. And again, it's made up of a weak base. And really in this case, this would be its conjugate acid. Yeah. Or the salt of its conjugate acid if you left the chloride. This is basically a salt. Remember, a salt's an ionic compound, right? So a positive, negative thing. Other than bases, if your buffer is made out of a weak acid and a conjugate base, that conjugate base mostly will have somebody from group 1. But if you start with a weak base like this, its partner will most likely have something like a chloride, a bromide, something like that on the negative side, because it will gain an H plus and become positive. All right, so let's talk about how it actually functions here to do it. So let's first talk about what happens when we actually add acid and base to a non-buffer solution. So if we add it to a non-buffer solution is something like water. Water is not a buffer. And if we add, let's just take HCl, which is a strong acid, and if we add that to water, what's going to happen in this particular case is much like maybe you saw in that experiment, you have some water, you're going to add some HCl. When I do that, because it's a strong acid, it is, as we've been talking about, going to 100% break apart into ions, into H plus and Cl minus. And in this case, we're going to have 100% of these guys. So basically what's going to happen is when you dump that HCl in, you're basically just dumping in a bunch of H pluses really quickly. So you're going to dump a bunch of free H pluses into that solution really, really quickly. What we're going to see is the concentration of H plus is going to rapidly increase because you added a bunch of H plus from that acid. The result of that is the pH is going to rapidly drop. So maybe this is water, which is maybe near 7. Maybe you got lucky, you got water at 7. And you add some HCl, you're going to see it could maybe go from 7 all the way down to like a pH of 2, a really big jump. This is equivalent to what you did in a lab, right? With the water or the sodium, I don't forget which one you did. I think you did water in yours. And you added maybe this like 1 or 2 drops of the HCl and the color changed, right? And that was just like 1 or 2 drops and you saw a 1 pH unit change just from a couple of drops. And that's because, again, you added a bunch of H plus really fast. So this would not be a buffer because you're going to see a pretty big swing in the pH. Now, what would happen if we added sodium hydroxide to water? So if we had our water here and we added some sodium hydroxide in there. Well, kind of the same idea. Sodium hydroxide, which is a strong base, will, again, much like the acid, 100% break apart into sodium ions and hydroxide ions. And essentially, what you're going to be doing in this solution is you'll add some sodium, which really won't do anything. It's just going to hang out and swim. But the important part here is you're going to dump a bunch of free OH minus into that solution. So very, very quickly, because this is going to 100% break apart, you're going to add a lot of hydroxide. So you're going to see a pretty big jump in the hydroxide concentration really, very quickly. If you remember, hydroxide and H plus are tied to one another. So when you do this and your hydroxide concentration jumps really high, what that does to your H plus concentration is it goes in the opposite direction. It starts to drop really quickly. And the result of that is you actually see the pH jump really high in this case because of that really quick influx of hydroxide into that solution. So maybe you go from a pH of 7 up to like a pH of 10 or 11 or something like that, depending on how much you put in there. Any questions on those there? So this is why we see really big changes in pH when we are adding acid or base to really a non-buffer solution. And that's because when we add acid, we're just adding a ton of H plus, and when we're adding base, we're adding a ton of OH minus, and those are going to cause really big jumps in the pH when we do that. Now, how does the buffer prevent that? Well, a buffer prevents that by, as we just talked about, having both things in the solution at the same time. It has an acid part and a base part. So let's take a look at a buffer. I'm going to do the one nobody else does because everybody else does acetic acid. So, and I don't want to write all those letters, so I'm going to go with hydrofluoric acid, and we'll do our sodium fluoride here. Once again, this is a buffer. This is a weak acid. I know that because it is not one of the 6 that are strong. And again, we don't want to be confused here. This is the salt of its conjugate base. And really, this is a salt, which means in solution, it's going to break apart into these 2 things. This is not important in terms of the buffer, but this here and this here, these are our 2 buffer components. This is our base part of our buffer, and this is our acid part of our buffer. And they're going to be able to stay in that solution once again because this is a weak acid, and it will be able to set up that equilibrium because it's a weak electrolyte. So what happens in this case is we have a beaker over here, right? And we dump our buffer in there, and it's going to set up this equilibrium because it's a weak electrolyte. It's going to stay in solution. And we will have, once again, as I mentioned, our acid part of our buffer and our base part of our buffer. And this is our buffer solution. So once again, in the solution, both of those things are going to be floating around in pretty good concentrations to begin with. So what we're going to do is going to add the same acid and base to this. So let's just say we took HCl now and we wanted to add it into our buffer. Because HCl is a strong acid, we are going to get a reaction. And if you had to guess, will the strong acid, HCl, will it react with the acid part of our buffer or the base part of our buffer? Yeah, because they're called acid-base reactions, so that's how the reaction is going to happen for sure. You've never heard of acid-acid reactions, really, or anything like that. So that's always what's going to happen here. So when we add this HCl to this buffer, it's actually going to react with the base part. And I'll keep the sodium on there if you want. You don't really need to, but you can keep the sodium. And if you do, what's going to happen is actually just a good old-fashioned double displacement reaction, right? We got 2 positive, negative guys, right? Positive, negative, positive, negative. We're just going to get a good old double displacement reaction here. And these 2 guys are going to end up together, and these 2 guys are going to end up together. That is going to create HF and NaCl in this case on our double displacement. If you left the sodium off, you would have, if you left the sodium off, you would have F minus here and just Cl minus over here. So you could do that if you want to leave the sodium out of the reaction. It's okay. So this is what's going to happen when we add this to our buffer. So let's take a look at what was produced in this reaction and why perhaps this is going to be okay. First off, we produce this guy right here, which is HF. HF, by the way, is part of the buffer to begin with, right? So we actually just created part of the buffer. And by the way, that always happens when you have a buffer and you add acid or base to it. You basically create the other part of the buffer. One gets used to react with it, the other gets created. That's not going to screw up the pH. This is sodium chloride. This is a neutral salt because it basically comes from a strong acid and a strong base, and it's not going to mess up the pH at all. It's that relationship we talked about that if it comes from something strong, it's going to be weak and not mess up the pH or go and do anything with it. But it's actually what we do not see here that we did see when we added it to water. What do we not see here that we saw when we added that HCl to water? What is not present on the right-hand side? That right there, yeah? There is no free H plus in this case, right? So we have no free H plus being made. And that's really important for the pH because if we are not making any additional H plus, that means the concentration of H plus is relatively constant. And if the concentration of H plus is relatively constant, the pH will also stay relatively constant as well. So I say relatively constant because, as I mentioned earlier, if you were actually following this with, say, like a pH meter or something like that, and you added acid to a buffer, the pH would move, but it would not jump giantly. So it may move down a little bit, but it won't go, as I talked about before, like a pH of 5 to like a pH of 2 or anything like that. It won't have a giant jump in pH. So what's really happening in this case is when you add the HCl, that is basically a source of H plus and Cl minus. And that H plus comes in and actually goes and finds the F minus, and it actually makes the other part of the buffer. The result of that is the amount of H plus you started with over here basically stays about the same. A little bit more is created because you make some HF, but in this case, the amount that you started with will basically stay relatively the same, and that will keep the pH relatively the same, and no really big jumps in pH. That is different than what happened when we added it to water. When we added it to water, you just loaded that thing up with H+, and that's going to cause a really big change in the concentration of H+ in there, and that's going to cause that really big pH change that you see. Question on that there. Now, what would happen in this case if we added our base to this buffer? So let's just say we had our same buffer here, and we're going to add our base. So we'll have our same buffer. It will set up its equilibrium here. Again, we have our acid part. We have our base part. And this again is our buffer. Once again, there is sodium floating around in there as well in this example, but it's not really doing much. But there would be sodium in both of these things. We're going to add our sodium hydroxide here. And this is going to add in. So if we add sodium hydroxide to our same buffer, as you might guess, it will react with the acid part, right? Again, that's going to give us our base acid reaction. So it's going to react with the acid part, and it's going to do a basic acid-base reaction, also a double displacement reaction, positive, negative, switching partners. That is going to create NaF, and H plus and OH minus is our friend water, basically, in this case. So we're going to create water in this case. So once again, as you can see, we actually made part of the buffer, just like we did above. And this always happens when you add acid or base to a buffer, you make basically the other part. We also made water, which is not going to screw up the pH. So it is exactly what we talked about above. It's actually what we do not see here that's important. And what we don't see here is if we look back at what happened when we added to water, when we added the sodium hydroxide to water, we created a ton of OH minus. And we created a ton of free OH minus in that solution. That had a drastic effect on the H plus concentration and also had a drastic effect on the pH. And in this case, no free OH minus was formed. And because the concentration of OH minus stays relatively constant, remember the H plus concentration is related, it will also stay relatively constant. And the result of that is, again, your pH will stay relatively constant as well. And what I mean again by that is same idea. If you added some base to a buffer and you followed the pH, you would see it go up a little bit. But again, you will not see these really big jumps in pH as you would see in water, for example. So what's happening in this case, when you add the sodium hydroxide, that's a source of sodium and hydroxide. It's actually the hydroxide here that's going to react with basically the H, and that's actually going to create more of the fluoride part in this case. So again, the way a buffer really works is because it has both of those components in the solution at the same time. It has an acid part and it has a base part. When you go to add additional acid or additional base to your buffer, what it's able to do is prevent the formation of free H plus. It's also able to prevent the formation of free OH minus when you add base. And because you're not adding, in the case of acid, more H plus to that solution or OH minus when you add base, it will keep the concentration of H plus relatively the same. And that is what allows it to resist changes in pH over a pretty good period of time, as long as you are made everything correctly. Now, you always make, as you can see in both of these equations, whenever you add an acid or a base to the buffer, the acid or base will react with one part of the buffer and then make the other part. So that is always, and that's why a buffer can kind of resist changes over a good period of time, because even though you're kind of using part of it, you're making some of the other part of it. So it's kind of regenerating, actually, if you kind of go back and forth, and you can make it last a pretty long time. Any questions first off on how that all works? So just graphically, if you were going to make a buffer, typically, you would make a buffer that has sort of a acid part and a base part that is, relatively about the same. And if you're wondering why, for example, I'll explain that in just a second. Actually, we'll talk about that in just 1 second. So if we were to add additional acid to this buffer, what's going to happen, as we saw, is that acid that you add is going to react with the base part of the buffer, and it's going to use some of it up. And it's going to create, actually, dramatically drawn there, more of the acid part of the buffer, and the base part will get used up a little bit of your buffer. If you add base to your buffer, it will react with the acid part, and it will make more of the base part. Again, dramatically drawn here, not to scale, base part. And it'll use up your acid part, right? And so it is sort of regenerating. There is what is referred to as a buffer capacity. There is a limit. There is a limit to how good a buffer will be. And when you make a buffer, you want to think about the molarity of your buffer. You also want to think about the molarity of your acid or base you may be adding to it. Let's just say, for example, I didn't follow instructions, which nobody would do in this class, I'm sure. And they add acid, and I just keep adding acid to this. What's going to happen as I continue to add acid to this? It is going to continuously eat up the base part, right? It's going to kind of continuously eat up the base part, continuously eat up the base part. Eventually, if you continue to add acid, or you add a way too strong acid to your buffer, you will blow right through the acid part, or right through the base part of the buffer. And if you continue to add acid at that point, now you're just going to be dumping in a bunch of H plus. And at that point, you will see a really big jump in the pH. And it's because you blew right through your buffer. And same thing will happen over here. If I continue to add base, I'll just continue to chew up this, and eventually I can blow through it. By the way, that is what happens in like your titration when you add 1 drop and it just changes color, as we talked about, and the pH jumps really big. In that buffer you did, in that titration you did, right around here, especially the second titration with the acetic acid, you actually made a buffer. So you didn't start with a buffer, but as you were doing that titration of acetic acid with sodium hydroxide, you actually created a buffer right around here. And then right around here, you blew through it because you kept adding base. And that's why you would see a jump in pH to the equivalence point. And that's why your indicator changed color so much, because there's a big influx really quickly of hydroxide into that solution as you're doing that titration, and you actually did it. By the way, when you do make a buffer, as I mentioned, the pH of the molarity of the buffer and the stuff you're adding is really important. This is also why it took you how many drops when you did the buffer the other day, like over 200? And that's because they set you up to do that way. Because if you remember how you created your buffer, you took how many milliliters of the sodium acetate? 25? And then of the acetic acid, you did just 5 milliliters, I think, right? Of the acetic acid, which was your buffer that you made. So when you started your experiment the other day, you actually had a ton more base part of your buffer than you did your acid part. And you were adding acid, right? Which meant you had a long way to go to see like basically a jump in pH, because you had a ton of the base part of your buffer in there, and it was able to resist a good amount of what you were dropping there. That's why you had to get up to like 300, 400 drops, or however many drops of craziness it was. Now, if you were to add base to that same buffer you made, you would actually see the pH move a lot quicker. It would take a lot less drops because there's a lot less of the acid part in there. Any questions on how a buffer works or what it's made out of? Okay. All right. That is chapter 16. Congratulations. We'll wrap